In 2022, the United States consumed 28.4 petawatts of electricity, accounting for 15% of the global electricity consumption. As a country with such high consumption, the source of electricity production has a global impact. In the last decade, while global CO2 emissions have risen by 6.6%, the United States has lowered their emissions by 11.3% over the same time period. While this statistic makes the United States stand out as an outlier against the rest of the world, the feasibility of this accomplishment and sustainability of continuing this trend is reviewed in this paper. Since 2019, the United States has been in an energy production surplus, meaning we generate more electricity than we consume. This not only gives the United States the opportunity to sell electricity to other countries and help them improve their renewable energy usage, but it also gives the United States the opportunity to decommission old, environmentally unfriendly power plants. The goal of this paper is to determine the feasibility of 3 different energy sources: wind power, hydropower, and solar power. We will determine how these 3 energy sources can be optimized to minimize cost, minimize emissions, minimize land area, and maximize reliability. The data collected for this research is divided into 3 of the most used renewable energy sources, and 3 parameters per energy source. First, wind power is the highest generated renewable energy source at 434.8 petawatt hours. Hydropower generation was the second highest renewable at 256 petawatt hours, and solar was the third most generated at 204.3 petawatt hours in 2022. These 3 energy sources are compared via cost per kilowatt hour, grams of CO2 per kilowatt hour, and kilowatt hours per unit area of land. These 3 parameters are then given an importance weighting, and adding to the complexity, a third dimension of time is added to the optimization, where the values of these 3 parameters are forecasted until 2035.
A genetic algorithm is used to optimize the mix of wind, hydro, and solar generation to minimize the objective function. Constraints ensure that total generation is greater than or equal to the total consumption. The objective function aims to minimize the environmental impact and costs associated with energy generation, and the constraint function enforces several conditions related to energy storage and consumption. For the purpose of this project, we focus on onshore medium-sized wind farms and the cost, emissions, and land area associated with them. A medium-sized wind farm has 20 turbines, and the carbon footprint of one turbine with an expected lifespan of 20 years is 4.9 grams of CO2 equivalent per kilowatt hour, and is expected to be 3.643 grams of CO2 equivalent per kilowatt hour by 2035. The cost of wind power is trending downwards and will only become cheaper as the years come by. Currently, the cost of wind power is roughly $2,200 per kilowatt hour, and it is forecasted to cost $1,500 per kilowatt hour by 2035. Wind farms require large land areas since there are several aerodynamic factors that affect the efficiency of turbines, such as turbulence and dirty air. So for our project, we broke it down to kilowatt hour per acre, and a wind farm produces 230 kilowatt hours per acre. The data was collected through peer-reviewed articles and government websites, such as the American Wind Energy Association and the U.S. Department of Energy.
There are 3 factors for our algorithm. First factor is the cost of a hydropower plant. Second factor is based on the total cost of area for a power plant. Third factor is carbon footage during the process of power generation. First factor is cost of the hydropower plant. The data of total capital cost per kilowatt is based on the Oak Ridge National Laboratory. It provided data from 1994 to 2020. This database provides historical capital and operating cost for large hydropower plant in the United States. And then based on this data, we made a linear regression curve prediction, which shows the power cost will be $0.3533 per kilowatt hour after 2035. Second factor is based on the total cost of area for a power plant. In order to make the prediction, we need to get the hydro constant, which is basically the total power generated divided total area, which we can get around 0.85. Third factor is carbon footage during the process of power generation, but since the hydropower generator power is too large, so there is no actual data for it. So I just based on the research which showed carbon footage is between 27.2 to 226 gram carbon dioxide per kilowatt hour. So I just choose the mean value, which is 126.6 gram carbon dioxide kilowatt per hour. So conclusion, based on the data, we know that hydropower might not be a good source for United States because the area consumption and the carbon emission during the production are not as good as other new renewable energy.
To determine the parameters of solar energy, historic data is forecasted into the future. This first plot shows the historic data of the cost of solar energy over time since 2010 and forecasts it until 2035. For emissions, a forecasted data source was found. And finally, for solar land area, the solar constant, 1,367.5 watts per meter squared, was used to relate the land area with the amount of energy generated. Then, the forecast of solar panel efficiency was used to calculate the final values.
For the approach, we here have a snippet of our code, and the MATLAB code performs an optimization for energy generation from wind, hydro, and solar sources, while considering factors like emissions, land area, and cost for each source. The goal is to find an optimal mix of these energy sources that minimizes the environmental impact and cost while meeting energy demand. For data generation, synthetic hourly data is generated for hydropower, including maintenance intervals, and wind and solar data are normalized to match a target mean.
The results of our optimization are as follows. Given the initial starting values stated earlier of each of the energy consumptions for each of the three sources, we can see that wind power maintains its lead, while solar power overtakes hydropower in energy generation. To confirm these findings, we turn to the hourly forecast. Zoomed out, we can see that wind power takes the lead as the highest generated energy source. Zooming into a 1-week time span, wind power is depicted with the blue line, storage usage is depicted with the green line, net usage is depicted with the cyan dotted line, and behind that is the consumption. At 0 are the hydro and solar power generation. This means that in these optimization findings, wind again took the lead as the number one energy source. As you can see, when the overall energy generation is less than the overall consumed, energy from the storage is used, shown in green. When the energy generated is above the energy used, energy is added to the storage and saved for these times when it is needed. This overall energy storage is minimized, as well as the total overall energy generation. In final, even with the deviation of generated energy compared to consumed energy, we were able to generate a result only 2.3% more energy generated than consumed.
Broader impact. This project anticipates a significant reduction in carbon emissions through the optimized use of wind, solar, and hydro energy. The transition to renewable sources aligns with global sustainability goals, contributing to a cleaner and healthier environment. Others can learn from our application of advanced optimization algorithms like FMINCON and genetic algorithms for renewable energy planning. These techniques can be applied to diverse optimization problems, providing a framework for solving complex challenges in other fields. Areas for improvement could be in the data set. Continuous data validation and incorporation of real-time data can enhance the accuracy of predictions and optimizations.